Okay, we'll start once again from the RCC structures. First topics in RCC is basically the shear. Okay, what are the defined treatment required for shear failure? Okay, in this course we are not going on details how the shear failures developed and why all those things. For more details, you can go for any kind of mechanics course. You will find more details on this. We will mainly checking what are the different types of shear failure or modes of shear failure occurs, and what are the location of those shear failure occurs, and for this what are the treatment required that we are going to check. Okay, so first part, if you see this first slide, is the failure modes due to shear. There are three modes of failure can occur in this case in RCC beam or column if you take. So these are basically, first one is the wave shear progresses along dotted line. This is first one is showing the wave shear. Okay, so this first one, if you look at this, this is basically called the wave shear. Okay, so this wave shear basically occurs as shown in these figures. Okay, it's basically some kind of crack that developed, and this crack is shown here, say around 45 degree. It can be less, 30 degree also. Okay, second one is the flexile tension, that is because of the yielding of the steel. Okay, and the third one is the flexile compression. Okay, in this case basically concrete crashes in compressions. Okay, so these are the some types of shear failure that occurs in case of a beam or any kind of member we will take. Okay, now we will see how the shear stress developed in case of say T section or L section or even in a rectangular sections. Okay, if we refer to the code books, this IS 456 2000s have given for uniform depth as well as for a uniformly varying depth of the sections what is the shear stress. Okay, if you look at this photograph, what I have shown here one rectangular section of width B and depth D. Okay, so what is the average shear stress? If you just see this, average shear stress is tau B. Okay, basically how the shear stress occur? If you see this, in case of a rectangular section, shear stress basically occurs in this fashion. Okay, maximum shear stress will occur at the center, and as shear stress will be minimum at the edge. Okay, if you say this is the neutral axis, so at the neutral axis the shear stress will be maximum, and it goes up, or as it is going downward, the shear stress will be minimum. Okay, so that means we can calculate here what is the tau B max. Okay, so in this location we can find out the maximum shear stress. Okay, this is called, this we can call as tau B max. Okay, and this is the average shear stress. Okay, we'll see we'll see how this actually occur. Okay, or the code books has given a guidelines. We'll directly take that formula in this case, because in this chapter we are not much interested on what are those derivation of all this, but rather than we are interested on how to apply those in our daily life problem. Okay, basically in our RCC structures. This is a T section. So in T section the shear stress diagram is, this is all rectangular sections, a T section. Okay, how the shear stress diagram occurs. Okay, this is the average distribution. Basically this one is the average distribution it is talking about. Okay, we are only interested on average distribution. Okay, okay, so if you look at this, see the code books in our this IRC IS 456 has given how to how to find out the nominal shear stress. Okay, so this is the equation given to find out the nominal shear stress. Tau B is denoted by nominal shear stress, and nominal shear stress tau B is equal to BU divided by BD. Here B is the breadth of the section, D is the effective depth, and BU is the shear force due to the design loads. Okay, and in case of a varying section, if you come down here, in case of varying section, what is that? value of the shear stress. Varying section we can find out the shear stress using this equation, that is tau b equal to bu plus minus mu by d tan beta divided by bd. Here this mu equal to bending moment at the section and b the angle between the top and bottom edge. Suppose you have a section in this fashion. Okay, so this is a section, right? So this is the angle. This angle is talking about the beta. Okay, and d is the effective depth and b is the breadth of the section, b is the shear force that is coming. Okay, now when to take positive sign and when to take negative sign, a guideline given in the code book is that the positive sign is applicable when the bending moment mu decreases numerically in the same direction as the effective depth increases. So if I go in this direction, effective depth is increasing. Now if bending moment in this direction decrease, okay, if I go this side, bending moment is decreasing, so I am showing it like that. Okay, if you go from this, or otherwise you can write down, if bending moment decrease but effective depth increase, okay, bending moment decrease and effective depth increase, then we will take positive sign. Fine. In other case, when the bending moment increase and effective depth also increase, then we will take negative sign. Okay, so remember it, when bending moment decrease but depth increase, we will take positive sign, and when bending moment increase as well as depth increase in the same direction, then we will take the negative sign. So this is how the plus minus sign of this for a varying depth. So for this type of sections we have to consider. Okay, if it is a constant depth, but that is basically if it is this type of sections where depth are constant, then nominal shear stress is equal to bu divided by bd. Okay, so that's a simple part. Okay, we need not to be confused on this. Okay, this is how we have to take. Okay, come to the next part. Even if we do not do any kind of or do not provide any kind of reinforcement on the concrete structure, still the reinforcement can carry some kind of shear reinforcement. That was obtained, experiment was carried out, and by the experiment it was found that without the reinforcement also still this concrete can carry some kind of shear. Okay, these shear strengths depend basically on the grade of the concrete. Okay, which grade of concrete is to be used. Okay, this shear strength depends on the grade of concrete and the percentage of tension reinforcement in the beam. Okay, and also it is found that the shear strength of reinforced concrete with the reinforcement is restricted to some maximum value, that is called tau c max. Okay, so Cookbook has given a guideline what is the maximum value of this shear reinforcement or shear stress without shear reinforcement, and what is the maximum value of shear stress with shear reinforcements. Okay, I will see this. Okay, this is the table that is available in the code book. Okay, it's a copy from the IS 456 2000s. Okay, what it is shown? It is shown here the design shear strength of concrete. If you open the code book IS 456 2000 and you go to clause number 26.2.2 and clause number 26.2.3, I have the table with me also from the code book, or you can, if you have the code book right now with you, you can open the code book, go to clause number 26.2.2. okay, then you will find that the information for this part is given to you. Okay, let me open also 26.2.2. Sorry, it's not clause number 26.2, it's clause number 40.3, okay, and 40.4. okay, there one table is given and table number 19. So that table number 19 is copied here, that is design of shear strength of concrete, that is denoted by tau c, and it is given in MPa, Newton per millimeter square. Okay, you can see that this is the percentage of longitudinal reinforcement, and depending on the defined grade of concrete, what will be the shear stress. This is called the design shear stress. Okay, so you can refer that. Then you go to the next table, that is table number 20. In table number 20, it is given about the maximum shear stress tau c max, that is also in terms of MPa, that is Newton per millimeter square, and the value of tau c max for defined grade of concretes are like that. Okay, for M20 grade of concrete, whatever be the percentage of the reinforcements, its value will be maximum of 2.8. okay, so and then like that for okay, it is given here 40 and above. So this basically this IS 456 is dealing up to a M40 grade of concrete, so that's why it is given like that. So, okay, so we'll go to the next part. See, I am just referring to the notes of NPTEL directly, so that we can refer this as quickly as possible rather than drawing all these things by myself. Okay, so just check it this, and you can refer to these notes also. Now next part, what are the support conditions for locating factored shear force? Okay, we'll see this part. So the critical shear force, depending on the support condition, how the critical shear force is locating at defined location. Okay, so first one, if you see the figure, in this figure, first one is what it is saying, that it is basically, you can see the shear force is very close to the support. In case of second figure, that is figure B, it is shown that the shear force is, or critical section for the shear force is at a distance of D, and the third one at figure C, it is shown that the critical shear force is at a distance of D on both sides. What exactly it is trying to say? Let us see for the first figure. First figure, it is saying that when the reaction in the direction of the applied shear introduces tension into the end region of the member, the shear force is to be computed at the face of the support of the member at that section. I am repeating once again what is saying, that when the reaction in the direction of the applied shear introduces tension into the end region of the member, so when it creates tension in this area, basically the upward pressure it is talking about, then the shear force is to be computed at the face of the support. Okay, so this is what it is shown here. Now come to the second category. When the reaction in the direction of the applied shear introduces compression into the end region of the member. Okay, if it introduced compression into the end region of the member, in that case the shear force is computed at a distance of D from the face of the support. Okay, so you can see this is at a distance of D from the side of the supports. Here it is what is that the support is at the center and both side the load is there, and both side the compression is generating. So therefore the critical section is at a distance of D from the both face of the support. Okay. Okay. If we refer to clause number 40.5 of the code book, it said that provide enhanced shear strength, or basically what I meant to say that we need to provide additional, or we have to take care of the section which is close to support due to the enhanced shear strength, due to the shear failure, because due to the failure of the plane steeper than 30 degree. Okay, so it is generally normally it is 30 degree, but sometimes the situation comes in such a way that this failure is more steep than 30 degree due to some location or due to some other reason. Okay, in this case it is code book has recommended to enhance the shear strength near the support. Okay, but in clause number 40.5.3 they have given a simplified approach rather than going in detail. So at this level the simplified approach on how to enhance the shear strength will be enough for this at this level, since we are not familiar with shear earlier. So, since it is the introduction of the shear, so we will be only talking about the simplified form how to provide. Okay. The codebook said that for beams carrying uniform loads, or where the principal load is located farther than 2D from the face of the support, the shear stress may be calculated at a section at a distance d, which is at a distance d from the face of the support. Then when it is talking about that, the shear stress will be calculated only at a distance of d from the face of the support. Okay. And whatever the value of tau c given in table number 19 that I have shown here, that is enough, and we have to take the appropriate shear stress at a distance of d from the support. Okay, that's what it is given the simplified approach. So we will be concentrating on the simplified approach rather than the detailed approach as discussed in clause number 40.5.1 and clause number 40.5.2. Okay, so we are not going to discuss on all these things. Okay, next we will see what is the minimum shear reinforcement required for a particular section. The minimum shear reinforcement, if you refer to codebook, in codebook it is given in clause number 26.5.1.5 and 26.5.1.6. Okay, it is saying that the minimum shear reinforcement in the form of stirrups shall be provided in such a way that ASB by BSB should be greater than or equal to 0.4 divided by 0.87 Fy. What are the meaning of the symbol? This Fy is the yield stress or characteristic strength of the reinforcements that we know. Yield stress of steel generally we use 415. B is the breadth of the beam. Okay, now come to this new term. One is given ASB and SB. Sorry, SB is the stirrup spacing along the length of the member. Okay, what is the spacing along the length of the member? That is, suppose we are providing the stirrups like that. Say this is a beam. Okay, in this beam we have provided some main reinforcements here. Then what we have to do? We have to provide the shear reinforcement on vertical direction like that. Okay, so shear reinforcements are generally provided like that. So these are also called stirrups. Okay, these are called stirrups. So here this SB is indicating that this is the spacing of the stirrups. Okay, so what is the spacing of the stirrups? That has been denoted by SB. Okay, so this SB here SB is denoted as the spacing of the stirrups. Okay, and then what is ASB? This ASB is talking about the area of the stirrup legs. Okay, suppose we have stirrups like that. This is called two leg stirrups. Okay, if you look at this, this is called two leg stirrups. So if I know the diameter of this stirrups is d, then while finding out the area, if it is a two leg stirrup, then the area will be pi d square by 2 multiplied by 2. Okay, so since it is two legged, two legs are there, so it is called two leg stirrup. So 2 times of the area we have to use here. Okay, so this is the minimum shear reinforcements. Okay, now if you refer this clause number 40.3 of the code book, clause number 40.3 is mentioning that the minimum shear reinforcement, when to provide the minimum shear reinforcement? Minimum shear reinforcement will be provided when the nominal shear stress is less than the design shear stress, that is the tau c given in table number 19. If nominal shear stress is less than the design shear stress as per the code books, then we will go for providing the shear. We are not going to provide the shear reinforcement, rather than we will provide the minimum shear reinforcement that I have shown you as per this clause. Minimum shear reinforcement as per these equations, whatever the shear reinforcements are coming, that is to be provided when tau b is less than tau c. Fine. Now, when to provide then shear reinforcement? That information, if you refer clause number 40.4 of the code book, what it is mentioned that when tau b is greater than tau c, when tau b is greater than tau c, we have to provide shear reinforcement. That means what I am saying to say is there, when this tau b is greater than tau c, we have to provide the shear reinforcement. Okay. So, how to provide the shear reinforcement? There are three forms of shear reinforcements are there. One is called vertical stirrups, then bent up bars along with the stirrups, and inclined stirrups. Vertical stirrups are basically sorry, that one I have shown earlier. This is the vertical stirrups. Okay, or if you see this is a beam, then in this beam whatever the reinforcements are provided, the transverse direction, these are called the vertical stirrups. Next one is a bent up bars along with stirrups. Bent up bars, you might have gone through your drawing classes, and many classes you might have find that some of the bars are bent up like that, and so this is the main reinforcement, then it is reached to some distance and then it has gone bent like that and it is got like that. So these bars are called bent up bars. Okay, you can provide these bent up bars in one location, or it can be provided to defined locations in a defined groups, or otherwise you can provide inclined stirrups. So in the beam we have the main reinforcement in this direction, I can provide the stirrups in inclined directions. Okay, so these are the three forms by which we can provide bent up by which we can take care of the requirements of shears. Okay. So for which shear we have to provide the shear reinforcement? Basically the additional amount, that is tau b minus tau c. This is the amount, this amount is denoted by BUS in the code book. For this amount we have to provide the shear reinforcements. Okay. So shear reinforcement is to be provided for an amount BUS which is equal to tau b minus tau c. Okay. Now another condition is given in the code books in the same code, that is clause number 40.4. What it is said that where bent up bars are provided, their contribution towards shear resistance shall not be more than half that of the total shear reinforcement. That means what it is saying that suppose I need a total shear reinforcement of BUS, then the contribution of this bent up bar should not be more than half of the BUS. Okay, that means suppose I need a shear reinforcement of BUS and I want to provide in terms of bent up bars, I am saying, then it is saying that the contribution for bent up bars should not be more than 50% of BUS. That means it can be a maximum, this BUS contribution with bent up bars can be a maximum of half of BUS. Okay, that's what is the Codel's guidelines and we have to follow that. Okay. So this equation and this equation is same. This it is written BUS equal to BU minus tau c BD, or this is same thing. What is tau b? Tau b is equal to BU divided by BD. Okay. And what is tau c? This is tau c. Now if you multiply this, or if you multiply this equation by BD and divide BD, then what will you get? Okay, then you will get the same things. Okay, this I said BUS is tau b minus tau c. Tau b minus tau c is basically the amount of shear. Now if you multiply this with the cross sectional area of the section, then it will give you the shear force in terms of force. This I said in terms of shear stress. Okay, so this unit is, you can say, MPa. When you multiply this with the area, that will give you the value in terms of force, that is, you can say it is in terms of Newton or kilonewtons. Okay, so same things, if you multiply this is giving you tau b into BD minus tau c into BD. Okay, what is tau b? Tau b is equal to BU upon BD, so you cancel it, BD get cancelled, so ultimately what is left here, or simply you can say tau b into BD is nothing but equal to BU, and tau c into BD is the same thing they have written here. Okay, so both have the same meanings. Okay, so either this or that equation, anyhow what we have to do, our objective is to know what is the additional shear force left for which we have to design the shear reinforcement, and that amount is BUS. Okay, and also it is said that this BUS amount cannot be more than 50% in case of bent up bars whenever we are providing the bent up bars. Okay, now let us see the remaining part. Remaining part means how to design this. Okay, now if you are using vertical stirrups, then vertical stirrups, the BUS, whatever the amount of shear force for which we have to do the shear reinforcement, that is to be calculated like that. In case of vertical stirrups, BUS equal to 0.87 FY D divided by SB. Okay, in kind of incline stirrups or a series of bars bent up at defined cross section. So it is mainly talking about when we are providing this type of incline stirrups, or you are providing the bent up bars at different cross section. This is one bent up bars and this is say another bent up bars at defined cross section. Then BUS equal to 0.87 FY D divided by SB into sin alpha plus cos alpha. Here alpha is talking about this angle alpha. Okay, and this BUS is the amount of shear force, SB is the spacing, here it is talking about this spacing. Okay, or if you take in this case, if you are providing the vertical stirrups, then this spacing would, or if you are providing the inclined stirrups like that, then spacing between the two stirrups. Okay, Fy meaning we know D is the effective depth, and what is ASB? ASB is the area of the shear reinforcements. Okay, ASB is the area of the shear reinforcement. Okay, and then it is said that when we are providing this shear reinforcement only in a single group, okay, so bent up bars we are providing in a together, in all the bent up bars together, then in that case what is to be done? In this case, since SB will not become, okay, so this spacing of the centers will not come, in that case we can use 0.87 Fy ASB sin alpha. This SB is not there, this is wrongly written. Okay, you can correct it. This will be 0.87 Fy ASB sin alpha. Okay, because here all are spaced together. Okay, whatever be the bar. So this angle is alpha here, this the area. Okay, so here SB will not come, so this spacing will not come here. Okay, wrongly it was written. So what is this ASB? Already it will total cross sectional area of the stirrup legs or bent up bars, whatever we are providing. SB is the spacing of the stirrups or spacing of the bent up bars groups. Okay, tau B is the nominal shear stress that we have used, symbol wherever. Okay, tau C is the, this is not T, this will be tau C. Okay, this we have used the symbol tau B, or this is tau C. Tau C is the design shear strength, B is the breadth of the member. Okay, Fy is the yield stress of the steel. Okay, A is the Na, alpha. Alpha is the angle between the inclined stirrups or bent up bars with the axis of the member. Okay, so these are the meaning of the symbols. Once we know this information, then we can apply them and we can find out the requirements of the shear stress. Okay, so whatever we have discussed, let us see how we can apply in a problem quickly and how we can find out the shear reinforcement required. Okay, suppose in this problem, so it is a simply supported beam given. Okay, so these dimensions are given. This is breadth is given 250, overall depth is given 500. So effective depth here it is 450, and clear cover, effective clear cover is given here 50. Okay, so we have given main reinforcement, 4 main reinforcement. This corner reinforcements are 25 mm and the center reinforcements are 20 dia, and in this case some minimum nominal reinforcement is given in the top side just to hold the shear reinforcement, that is given 2 numbers of 12 dia bar. Okay, so determine the shear reinforcement of the simply supported beam of effective span is given 8 meter whose cross section is, okay, so effective span here is given 8 meter. Okay, factored shear force, that is Bu is given to us, and that value is given 250 kilonewton. Okay, use M20 grade concrete and Fe 415 steel. Let us see how we can. Okay, so what is to be done? Our first job is to find out the area of the main reinforcement. So in main reinforcement, if you see the figure, it was given 2 number of 25 dia and 2 number of 20 dia. Okay, so if you do the calculation, it will give the AST and divided by the effective cross section area, that is B into small d. So that is giving you the percentage. Here it is done. Okay, total area of the AST is 1609. Just do the calculation, then multiply with this by 100 and divide it by B into D. Okay, that's what we need in our table number 19. Okay, table number 19, if you see that, open your code book and see the table number 19 that is given in page number 73. First term is written 100 into AS divided by BD. This A is the area AST, this is 100 divided by B into D. Okay, so this value is coming 1.43. So once this value is coming 1.43, now you have to refer the code book. Okay, in code book, what is that? The table number 19. If we refer code book table number 19, okay, and it is given in page number 73, table number 19, okay, and it is given in page number 73. We can do the interpolation to find out the tau c. Okay, since in our case we are using which grade of concrete? M, you just refer this M20 grade of concrete, it is said. So for M20 grade of concrete, we have to find out the value of tau c. Now see, for our percentage is 1.43. In the code book we have a percentage of 1.25 and we have percentage of 1.5. For M20 grade of concrete, the tau c values are given as 0. If you see this, 0.67 and 0.72. Okay, so these are the two values given. Our target value is how much? 1.43. So you do the interpolation. I am sure you know how to do the interpolation, or just quickly I am showing you what is the interpolation. Here it will be 0.67 plus 0.72 minus 0.67 divided by 1.5 minus 1.25 multiplied by, what is our target? Target is 1.43 minus how much already we have written, for which we have written for 1.25. Okay, if you do this calculation, this value is coming out 0.706. That's what shown here, that this value is 0.706. Okay, so this is the tau c value. Now you have to, that is the design shear stress. Now you have to find out the nominal shear stress. What is the nominal shear stress? Nominal shear stress as per the code book, it is BU divided by BD. BU in the problem given 250 kilonewtons, so 250 into 10 to the power 3 divided by B into D. B is given 250, D is given 450. This value is coming how much? 2.22 MPa. Okay, so also you can see what is the tau c max. If you see the code book, the tau c max for M20 grade of concrete is given 2.8 MPa. You can refer table number 20. Okay, of the code book given in page number 73. So this value is, so no doubt this value is less than tau c max, so it's fine. This value is also less than tau c max, so it's accepted. Okay, but if you see here, tau b is greater than tau c. Both are less than tau c max, and that is the accepted one, that though both must be less than or equal to tau c max. But here tau b is greater than tau c. So if tau b is greater than tau c, what we have to do? Do I need to provide shear reinforcement or not? Yes, because code book saying that when tau b is less than tau c, the main reinforcement is enough. We don't need to provide any shear reinforcement. But still we will be providing the minimum shear reinforcement. But whenever tau b is greater than tau c, we must design the shear reinforcement. That's what you can see here. Here tau b is greater than tau c, so shear reinforcement is to be provided. So shear reinforcement is to be provided for how much shear? That shear we can calculate using this. Bu is equal to Bu minus tau c BD, or you can write Bu is equal to tau b minus tau c whole into BD. Okay, whatever. So Bu is 250 kilonewton and tau c already we have calculated, multiplied by the BD. So it is giving. Okay, so there is a total amount of reinforcement shear force for which we have to provide the shear reinforcement is 170.575. So this is the amount of shear force for which we have to provide the shear reinforcement. Now it's depend on the designer, or it's if nothing is mentioned in the problem, or if something is mentioned how to provide, then as per the given problem we have to do. Since in this problem nothing is mentioned, so we can decide by our own. Okay, so what we are doing here? Here we are providing 8 mm dia 2-legged vertical stirrups. Okay, so it is basically, this is how we are providing. This vertical stirrups we are providing with 8 mm dia and 2 legs. So, this is one leg and this is another leg. So, what is the area? So, here I said area will be 2 into pi by 4 into d square. D here we are taking how much? 8 mm. Okay. So, you do the calculation, this value is coming out 100 mm square approximately. This fraction is limit. So, once you know the ASB, then we can calculate the SB. What was our equation? Equation was BUS is equal to 0.87 Fy ASBD divided by SB. From there I can calculate the SB. SB equal to 0.87 Fy ASBD divided by BUS. BUS is known to us. Just now we have calculated. Okay, this is the value. Fy is how much? 415 it is said. ASB we have calculated here how much? 100, and D is the effective depth of the beam. If you put it, it is coming out how much? 95.2 mm. So, it is saying that you need to provide a spacing of minimum 95 mm. Okay. Now, what you have to do? We have to check it whether it is satisfying the minimum reinforcement, shear reinforcement criteria. Okay. Now, if we change it, okay, let us do this way also. If we change, rather than providing 8 mm, let us say we are providing 10 mm. So, if you provide 10 mm, same equation you can use, rather than only what you have to do is that we have to change the area here. So, I have changed the area. So, this value is coming 149.54 here. Okay. Now, two spacing we got, one we got 95, another we got 157. Now, the codebook has given a guideline that what should be the maximum spacing for shear reinforcement. Okay, that I have not mentioned earlier. If you see clause number 26.5.1.5 of IS 456, they said that the maximum spacing should be 0.75 D. Okay. So, just refer that, you will find out the guidelines what is given on that. For your reference purpose, I will just read what is written there. It is written like the maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75 D for vertical stirrups and D for inclined stirrups at 45 degree, wherever D is the effective depth of the section under consideration. However, in no case shall the spacing be exceed 300 mm. That means it is said that the spacing shall not be more than, in any case it shall not be more than 300 mm, or if it is a vertical stirrup, then it cannot be more than 0.75 D, or if it is a inclined stirrups, then it cannot be more than D. Okay. So, what we can say that means it shall not be more than 0.75 D or 300 mm, whichever is minimum. So, 300 mm is the minimum. So, maximum sorry, it is saying that the maximum spacing we can provide is 300 mm. Next, what we have to do? We have to check what is the minimum spacing to be provided. Okay. So, for that we have to refer to the clause that I have shown you earlier. It is 26.5.1.6. If we refer there, they have given the equation. What was that equation? That equation is, one minute, that equation is ASB divided by BSB greater than or equal to 0.4 by 0.87 Fy. Okay. So, this SB, what should be the minimum SB? Minimum SB will be equal to ASB ASB, you can calculate from here ASB also, or you can other way also we can do, you can calculate here SB also. Okay, both we can do. Here what I have is done here is that ASB was calculated. I will show you the SB also. So, what is the ASB? ASB minimum will is 0.4 BSB divided by 0.87 Fy. So, B is 250 in our case, and SB you can apply here. You see in this case what we have calculated SB we have calculated here 149.54. So, it is taken as 145, we can apply it, and we can see that if we provide a spacing of 145, then we need to provide a minimum shear reinforcement area of 40.16. How much we are providing? We are providing how much? This 145 is basically taken in case of 10 mm. So, even if you provide 10 mm legs, then minimum area we are providing is 157 mm square, but actually we are supposed to provide 40. So, this is one way of checking. Other way of checking, that we can check the SB. That means what I am trying to say is that we can find out what should be the SB. What it is saying, that if I write down this equation in other way, so what will be the SB? SB must be less than, in this way also I can write 0. What will be 0.87 into Fy into ASB. I can write like that, divided by 0.4 B. Okay. So, that indicates how much it will be. You can put all the values 0.87 Fy. Now, ASB you put. Now, if you take 8 mm, then what was your ASB? Last page you check, that was 100 mm square. If you take 10 mm, then what was the ASB? That was 150. So, any one of this you put, take with 150, say this is 157, we are using 10 mm, then 0.87 into 415 divided by 0.4 into B is how much? 250. You do this calculation, you will find out what is the maximum spacing below that we can provide as per these guidelines. Okay. See here, this value is coming 567. That means we have to provide a spacing which must be less than 567 whenever we are providing an area of 157. And what we are providing, we have calculated. See, if you see the last page, we have calculated how much is to be provided, 95. So, 95 is enough, because we can go up to 567, but the maximum spacing is saying you provide 300, and as per this equation, this value, that if we provide even 145, that is okay, because 145 is also 100% satisfying the minimum reinforcement criteria. We are providing 145, maximum spacing how much we can give, 300, and as per this equation saying that even if I provide less than 567, that is also okay. So, even if you take this 10 mm dia, fine, you can check with 8 mm dia also by yourself, that you will find the spacing is coming less than that. Okay. So, finally, what we can say, that we can provide 10 mm dia 2-leg vertical stirrups at the rate of 145 mm center to center. That is very fine and accepted. Okay. So, this is how you can do the problem. Simple thing is that you decide yourself that which type of stirrups you are going to provide. Suppose in this problem it was saying that this bent up bars are also provided. That means bent up bars will take maximum 50%. So, first we will calculate for bent up bars how much shear force is taken care by bent up bars, that we have to calculate, and then we have to check that this value cannot be more than 50% of the BUS. Suppose in this problem, what was our BUS? If we just go back in the problem, our BUS was 170.57. That means if I provide in this case bent up bars, then how much shear I can give to the bent up bars? That will be half of that. That means 85.29, right? 85.29 kilonewton of shear that I can give to the bent up bars, and remaining is to be taken. This I can give to the bent up bars, but the remaining 85.29 I have to either provide inclined stirrups or I have to provide vertical stirrups. Okay. So, similar simple steps, same equations are there, you can use the equation, you can, okay. This way you can do some more practice on how to provide the shears. Basically, whenever we go for a design of any kind of, say it is a single reinforced sections or double reinforcement, whatever it is, everywhere we need to provide the shear reinforcement. Since initially we do not know what is shear reinforcement, so we do not provide, okay, but actually we everywhere we have to provide shear reinforcement. So, we have to check by this, wherever the tau b is coming less than tau c, it's not like that we should not provide, still we should provide the shear reinforcement. How we should provide? We should provide based on these guidelines. Okay, that means we should provide the minimum shear reinforcement in that case also. Okay, that's it about the shear reinforcements. So, next chapter will come with, next lecture will come with the with a different topics.